let us discuss the BST deletion here, binary search tree deletion. Okay, so it's the code that we have just discussed during the lab session, but I made one small change. So this is the delete function, which takes one node as the pointer to a node as argument. Okay, generally takes the root node as the argument and the node to be deleted. Okay, there are some other pointers we are using like traverse, previous, minimum, ISUC to find the in-order successor, I predecessor to find the in-order predecessor, node to be deleted, a pointer to that, and a pointer to the parent of the node to be deleted. Okay, right. So initially all these are say is null. Okay. So then we are making traverse to point to root and previous to point to null. If traverse is null, then we say that the tree is empty. Okay. In this case, the tree is empty. Otherwise, traverse equal to start, or you can say root. Okay, whatever it may be. So let me keep it as root. While traverse not equal to null, here we are checking if traverse is equal to the key that we want to delete. In that case, if this is the one that we want to delete, then we are storing previous node underscore del is equal to pre. Okay, right? So initially pre is null because this is what root node. So root node does not have, if the root node is the one that you want to delete, then it does not have any previous. Okay, and the node to be deleted is traverse. Like that we are marking, we are not coming out. The reason why we are not coming out is when you perform in-order successor or in-order predecessor, when you copy that value to the other node, okay, and then when you want to delete that actual in-order successor, then two nodes will be having the same value. Now we want to reach the actual node which is to be deleted, which is at the lower level, right? So that we continue this to happen until we reach the node with the key in the lowest level of the tree, right? Okay, fine. So after this, so this is one separate if. After this, there is another if. Here we are checking if yes greater than or equal to traverse arrow key. So why we are using greater than or equal to, you may wonder. Again, it's for the same reason. Because when you have in order, for example, if you want to delete a particular node, and if you have replaced it with its in-order successor, first we will check for its in-order successor. If there is an in-order successor, we will replace with that in-order successor. If there is no in-order successor, then only we will replace with the in-order predecessor. Okay. So we are checking whether that particular, I mean, whether the value yes, okay, whether the value yes is greater than or equal to traverse arrow key or not. Okay, even if it is equal to, then we want to move to right. Okay, but there is another condition. When you can move to right, only if the right child is not null. Okay, if the right child is not null, only if the right child is not null. In the previous iteration, you might have selected the in-order successor. Otherwise, you would have selected in-order predecessor, right? So in that case, previous becomes traverse and traverse becomes traverse as a right child. Else, if this is not satisfied, okay, when this will not be satisfied, only if there is no right child. If there is no right child, this will not be satisfied. Okay, right? Then we make the pointer to move to the left. It means then it is replaced with the, I mean the left successor, or if it is the first iteration, it will go to the left. Okay, right. So once you come out of this loop, you have a pointer to the node to be deleted. Okay. If there is no such pointer, if node to be deleted is null, then it means that there is no such key exists. Okay. Otherwise what we are doing, this is the node to be deleted. Now traverse is going to point to the node to be deleted. Okay, fine. So next we are checking. So this is the, now we have identified the node to be deleted, but you have to check if it is a leaf node, you can delete directly. Otherwise, you have to replace with either in-order successor or in-order predecessor. So in our case, first we will try to replace with the in-order successor. So we are checking whether that node is having a right child or not. If it is having the right child, then we are finding its in order successor by this function minimum. To the function minimum, we are passing its right child. Okay, and this nodes key will be replaced with this in order successors key. Then again, this in order successor should be deleted. Again, it can be deleted directly only if it is a leaf node. Okay, so once again we are calling the delete function. We are passing root, and now we want to delete this particular the node with this particular key. Okay, so suppose if the node to be deleted that does not have a right child, then we are checking whether it is having a left child or not. If it is having a left child, then we are finding the in order predecessor, okay, of that particular node. In order predecessor is the highest node of the left subtree. So we are finding the maximum element from the left subtree, traverse arrow left child, okay, and traverse arrow key is replaced with the predecessor key. Then again we are calling the root in a recursive fashion, okay. If these two conditions were not satisfied, okay, it means traverse the node to be deleted does not have a right child and also it does not have a left child. In that case, it's a leaf node. Then you can delete it directly. So here sometimes we may want to delete the root node itself. In that case, it means that root node itself the leaf node. Okay. So how could we check that? For that you have to check the previous node to be deleted. Is it null or not? If the previous node to be deleted is null, then we make root to null. It means there is nothing to delete. Okay, and then also you can print that tree is empty. You can say that the tree is empty. Okay, and you can return because there is nothing else to do because the totally same so empty one, right? Otherwise, if previous underscore node underscore del is not equal to null, it means that there is, even after deleting this node, the current node which we are going to delete, that is a leaf node, but it has some parent. Okay, so we need to find whether it is the right child of that parent or left child of the parent. So parent is nothing but previous underscore node underscore del. If its right child is equal to traverse, then previous underscore node underscore del have right child will be null. Okay, because traverse is the one we want to delete. Otherwise, we will make previous underscore node underscore del arrow left child as null, and then we free the pointer for traverse, right? So this is the logic. Okay, so here in the main function I am calling delete of root of s, okay, and then I mean in order of root, okay. So it will delete that particular key. Here we are taking the key of the node to be deleted, and we are passing it to this function delete the root node and the s to be deleted. After deleting, we are displaying it in order fashion. Okay. Then this logic is to delete more nodes. Okay. While x not equal to 0, here I am asking the user like enter the node to be deleted, and then we are deleting it, and then we are displaying it in order fashion. Again, we are asking, do you want to delete one more node? So that is x. Okay. So initially I can set here x is equal to 1. So it means it is not 0. So as long as user is not giving 0, it will keep deleting. Okay. So this is the whole logic. Right. Let me execute this program. So here there is some extra insertion. I am making it comment. Okay. Save it. Compile. Execute. Okay, say I want to create a tree with 10 nodes. Number of nodes I am giving 10. Okay, so these are the nodes 8, 3, 10, 1, 6, 14, 4, 7, 13, and 15. Okay, so this is the tree in order style. Okay, so enter the node to be searched. Say I am giving 14. 14 is there. Now enter the node to be deleted. 8 is the root of the tree. I am going to give 8. So this is the state after deleting 8. Okay. So when you delete 8, 10 will replace 8. Okay. And the previously whatever 10 that will be replaced by 13. Okay. So that it is coming like this, right? So now the root is 10. Okay. Then say I want to delete 10. Okay. So this is after deleting 10. 1, 3, 4, 6, 7. So do you want to delete one more node? Yes. Say I am deleting 7. So this is after deleting 7. Do you want to delete one more node? Yes. Say I am deleting 13. This is after deleting 13. Do you want to delete one more? Yes. Say 6. This is after deleting 6. Do you want to delete one more? Yes. Say 4. This is after deleting 4. Do you want to delete one more? Yes. Say 14. This is after deleting 14. Do you want to delete one more? Yes. Say 15. This is after deleting 15. 1 and 3. One more? Yes. Say 1. So this is after deleting 1. Only 3 is there. Do you want to delete one more? Yes. Say 3. So after deleting 3, you can say that 3 is empty. Okay? But still it is asking we want to delete one more. But we know that there is nothing to delete. So I will give 0. Okay? That's it about BST. So you can try this code. Fine. Thank you.